Lorentz invariance, we mentioned that the Lorentz symmetry is not manifest, right? After quantization, there is no guarantee that the Lorentz symmetry will be satisfied. So now I'm gonna use that, and I said we can actually, under certain condition, we can actually get back the Lorentz symmetry. So the point here is, if we demand the Lorentz symmetry, if we want to bring back the Lorentz symmetry, then we see that the only way it works is if the first excited state is a massless state. Otherwise, it doesn't fit. It doesn't give us the right fits with the right symmetry. Okay, so the upshot here is then to preserve the Lorentz symmetry, we need the first excited states to be the massless states. And look at something here. So if it's a massless state, so remember that our level matching condition, our mass condition was something like this. So if we want this to be 0, what do we get? So we get 26 dimensions, space-time dimensions, right? That's what we call the critical dimensions of space-time. One final comment. So as I said, these guys, this alpha minus I, alpha minus I triple j, 0p. Now, since the dimension is 26, so they transform as 24 times 10 to the power 24 representation of the SO24. So if we, and it has actually, it can be decomposed into 3 irreducible representation. So the first one is, again, as I mentioned earlier, this traceless symmetric tensor, rank 2. Then there is a antisymmetric part, and then there is a trace part, right, which is basically some singlet, the trace part. Now this corresponds to this metric tensor. This corresponds to some antisymmetric tensor field, two-form field, which you call the Kalb-Ramond field. And this is, of course, you can see that this is what we call the metric, and this is what we call the dilaton, the scalar field. Now, it turns out this part can be identified as a massless, so it's again, our first excited are massless, right? So it's a massless particle, a spin 2 particle. So this is basically what we call the graviton. Okay? And of course, we can confirm the helicity and so on to confirm that this is graviton, spin 2. So the first massless spectrum of the string has 3 massless. Sorry, the first excited state of the spectrum has 3 types of particles. We get gravitons, and this is basically some sort of gauge field, and also a dilaton, scalar field. Okay, I'm going to stop here. I hope I didn't take too much.
Perfect, perfect. So thank you so much, and so
sure,
I'll just stop the recording and